two together and then you'd be really
They
happy.
were in our class.
Who's the lady in the background?
And Belinda.
Why she got words coming from her head? So you lied.
No, I just wanted to. Is that what crap you guys would give me?
No, I didn't cheat, I was just using my resources.
Basic concepts of probability. So what we're going to cover, and I wouldn't write most of this down and just listen. We'll write down some stuff here in a minute. Identify sample spaces of a probability experiment. Identify simple events. Use the fundamental counting principle. We'll talk about all that today. Different kinds of probability: classical, empirical, and subjective. Does anybody know what the word subjective means?
It only applies to a certain subset of things.
All right, so it's just like, this is the way it is. And we'll talk a lot about that. Subjective is, we're doing probability, I'm saying, there's a 57% chance that you pass that test that we just took. Well, that's maybe applying what I've learned from the past to you guys. Does that mean it applies to you really? No, so that's what makes it subjective. Determine the probability of a complement. So that's not hard, and if we happen not to get to it, I'm going to explain it right now. What's the probability of drawing a queen out of a deck of cards? 4 out of 52. What's the probability of not drawing a queen out of a deck of cards? 48 out of 52. Those two are complements, because together they make the whole probability, all right, the whole set. Use a tree diagram. We're not going to use a tree diagram because I don't like drawing a whole lot, but you need to know what they are, all right? Tree diagram is just this. If I had the probability of drawing a queen and we were only drawing once, I don't know, let's do something different.
4 to 52. 4 to 52.
If we were doing a pizza, let's say we were doing a pizza, and you had 3 different crusts, 5 different toppings, and 2 different cheeses. All right, to choose from. So the first thing we do is put the crust. Crust 1, crust 2, crust 3. Now, for crust 1, I could have what? The first topping. I could have the second topping. I could have the third topping. I could have the fourth topping. I could have the fifth topping. Then for crust 1 with topping 1, I could have the first cheese. I could have the second cheese. That's a tree diagram. List them all off, and then we say crust 1, first topping, first cheese. That would be one of our possible outcomes. Notice that gets real long real quick, and I don't like drawing on stuff like that, and I especially don't like trying to grade your papers looking at stuff like that. Oops. Inferential statistics, using data to analyze or draw conclusions about a population. You guys have that happen to you all the time and you don't know it. A probability experiment, I'm going to put these up here real quick. Again, I would not write all this down word for word, abbreviate stuff, make stuff easier on yourself as you're writing it down. Okay, did I leave my water sitting on your desk?
No, that's mine.
That's yours? All right, oh, there it is. I just thought I was leaving my stuff sitting in your way because your desk was close to mine. Somehow I left this sitting over there. Probability experiment. and we used to do stuff when I was younger and not so old and crotchety. But we'd get out like a penny, and I'd have you sit there, you and a partner, and flip a penny like 100 times and see what you came up with. Now, if you flip a penny 100 times, what should you come up with? 50 heads and 50 tails. Do you think that usually happens? No. All right, that'd be the experiment. See what does happen. What do you think would happen if we added up everybody's flips in the classroom? It'd probably get really, really close to being 50-50. And if we just kept doing it and kept doing it over time, guess what would happen? We'd get closer and closer and closer to being 50 heads and 50 tails, or 50% heads and 50% tails. An outcome is the result of a single trial. So if I flip that coin once, that outcome, whether it's a head or a tail, is that result of that single trial. Sample space. Sample space is the set of all possible outcomes. If I'm looking at my pizzas up there, sample space would be if I did that whole list and wrote everything that I could possibly get out at the bottom. Now, a sample space, I'm not going to have you list sample spaces that are that long and drawn out. What would the sample space be for flipping a coin? Heads or tails. What would the sample space be for drawing a number out of a hat from 1 to 10? It'd be what would all the numbers be in there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the sample space. What could happen? An event consists of one or more outcomes and is a subset of the sample space. So one event for our pizzas up there is we could pick crust 1, topping 1, and cheese 1. That's one possible event. Does everybody know what a subset is? Give me a subset of our classroom here.
Football players.
Football players. All right, that could be a subset. Brandon and Riley would be a subset.
Brandon.
Did I say it wrong?
Sure.
Brandon. Brendan, sorry.
He's the red town. You thought he was Brandon Phillips.
Brandon Phillips.
That looks similar.
They're very similar. They're both short.
A tree diagram. I don't know what you want to do, but so that you know what a tree diagram looks like, we're not going to do a whole lot with them, but this is a tree diagram. All right? So this one, it looks like we were picking our lunch. You got to pick what kind of drink you want, whether you want a juice or a soda. Then you got to pick what kind of bread you wanted, white bread, rye bread, or a bagel. And then you pick what kind of sandwich you wanted, pastrami, cheese, roast beef, or turkey. All right? And then this out here is our sample space. This is the list of our sample space. And if Ben gets on my nerves like he usually does, then maybe I will have you do a whole bunch of sample spaces on the next test and just have them all written out like that. Wouldn't that be fun?
Blast.
Give me one possible outcome for the lunch you picked.
Soda white cheese.
Soda white cheese. How many total outcomes are there? 24. Anybody agree with that? So what's the chance that you pick, or what's the probability that you picked a soda with white bread and just cheese on it? 1 out of 24. All right, so that's a tree diagram. Just know what a tree diagram looks like. Be able to draw one. None of them that we do will probably be even this long. This one's not all that real long, but none of them will be probably even this long if we do one. Be something a little shorter. Soda, white, and turkey. What's the probability that you pick soda, white, and turkey on it? 1 out of 24. We just did something like that. Probability experiments. Probability experiment, if we roll a die and we want to get a 3, our sample space is, we could get a 1, we could get a 2, we could get a 3, a 4, a 5, or a 6. The probability that we get a 3 is what? 1 out of 6. What's the probability that you get an even number? 3 out of 6, which would reduce down to 1/2. 1/2. Now, I heard some of you say like 50% would be right. I wouldn't start changing things to 50% until we actually need to. So 1 out of 2 is probably better to look at than 50%. All right? Now, if we have something like 632 out of 7,920, we probably don't want that. Then that's when we probably change it, divide it on our calculator and change it to a percentage. Okay? But if it's something fairly easy, we probably want to leave it that way. Because that 1 out of 2 tells us a lot about the probability. It tells us how many favorable outcomes are there. 1. And we're going to do this event how many times to get that 1? 2. So 1 out of every 2 times, we're going to win. Or get what we want. Probability experiment consists of tossing a coin and then rolling a 6-sided die. Describe the sample space. So what is the sample space? If I toss this coin and roll a 6-sided die, what could I get?
You can get head.
Head,
One.
and a 1,
Yeah.
then what?
Head 2.
Head 2,
Head 3.
head 3. Notice Mr. Simpson's very, very intelligent because he's going in some kind of order, right? Not just jumping all over the place. I could get a head 5, a tail 7, you can't get a tail 7. What's next?
Heads 4. 5. 6.
Is that all of our sample space?
No.
No, what else could we get?
Tails. And
That's our sample space. Now, if we use the 20-sided die, what would we have to do? A lot more of them, right? So that's our sample space. How many total outcomes are there? 12. So what's the probability of getting a tail 2? 1 out of 12. What's the probability of getting a tail and an even number? 3 out of 12. Favorable over total.
Wouldn't it be 6? 6 out of 12?
Tail.
Oh, tail even, okay.
What'd you think?
I thought you meant just even.
So the tree diagram would look something like this. If we wanted to make a tree diagram, again, I think this would be a head, that'd be a tail, not the pictures. If you start drawing pictures that look like that, then you're wasting a whole bunch of time that you shouldn't be. A simple event. A simple event is an event that consists of a single outcome. An event that consists of more than one outcome is not a simple event. So, when we just did that, if we tossed it and we said we want to get a head and a 1, that's a single event. Because there was only one time we could get a head and a 1. If we said we wanted a tail and an even number, now that's no longer a simple event because there's more than one thing there. So a head and a 3 would be a simple event. A head and an even number, sorry I said tail and an even number on the other one. But it doesn't matter, same thing. Not a simple event. You roll a 6-sided die, event B is rolling at least a 4. Is that a simple event or not a simple event? At least a 4. Would that be simple or not? Not, because you could get a
Could get one or two.
Now, hold on, because we want at least a 4. 4, 5, and 6. So is that simple or not? Not simple. But we could get 4, 5, or 6. All right. Fundamental counting principle. Very, very important that you understand the fundamental counting principle. I'll give you a second to copy some of this down. Main thing with fundamental counting principle is maybe you might want to write it like this. Whatever the first thing is, whatever the second thing is, whatever the third thing is. This is when you're doing more than one thing. Number of outcomes times number of outcomes for this one times number of outcomes for that one. Nothing hard about fundamental counting principle. It's very, very simple. Instead of making some big long drawn out tree diagram, we're multiplying the possible outcomes for each thing together to get the total possible outcomes. It's not hard, it's just hard to explain, and that's why it's like 2 sentences long there to explain it. But once you write it down and you understand it, then you probably won't go think, why did I write all that down? That was stupid. So Ebersole got up this morning. I know, Brendan, I look spectacular. So I got up this morning, I picked out this outfit. In my closet, I've got $32 ties. It's probably more than that, but I'll just make that numbers. I've got 4 shirts. Are you making fun of me? Are you saying?
I'm just making it easier for you.
It's not easy for me. You're the one doing the
White.
math. I've got 12 shirts. And
A pair of white ones and then khakis.
And I've got 8 pairs of pants. And guarantee none of those numbers are correct. I probably got about 15 pairs of pants and about 30 shirts. None of them fit me anymore, so I don't know. They keep shrinking around this part here. The whole shirt doesn't shrink. They still fit me around the shoulders.
The washer must be doing
I know, the washer is stupid thing. All we do to find the total possible outcomes, different outfits I could have made this morning, multiply those 3 together. Is that something you'd really want to make a tree diagram for?
No.
Absolutely not. How many did it say?
3072.
3,072?
Yeah.
So 3,072 different outfits
I
that
don't
I
have
could have put
anything to
on.
wear.
What was the probability that I selected this one? 1 out of 3,072.
There you go.
Now, when we do that, that's 1, somebody grab your calculator again, what's 1 divided by 3,072?
Scientific.
To give you some scientific notation?
Yeah.
What's it say?
3.2552.
Yeah, 3.255, so we'll say 26 times what? So that E on your calculator
Times 10 to the
is
negative.
times 10 to the negative 4th? Is that what you said?
0.
So that tells us we're going to bump this decimal over how many places?
Negative. That left
4 places, right? So how many zeros? 3. Now, if we wanna change that to a percentage, we're gonna bump it back 2 places this way. So what's the probability that I picked out this exact outfit? Is it 3%? No, it's 3/100%. Alright, so the probability that I picked out this outfit is less than even half a percentage. Alright, it's 3/100%.
That's a different outfit for like 8.5 years.
Right. So is there a whole lot of chance that I ever pick out this outfit again?
What if you like it?
Yeah.
I mean, if I like it, then yeah, but otherwise, probably not. It's not a real good chance that I pick out the same outfit over and over and over again. Even though I probably do, because what ends up happening is my clothes get washed, and then instead of putting them away, they're laying there in a basket, and I just grab them right out of the basket again instead of doing the work to hang them back up and do all that. You guys don't do that, do you?
I don't do that.
Huh?
I put mine on.
You put your laundry up?
Oh, here you go.
I'll wash
I'm
them
being that
and then
guy.
put it up.
Go, Superman.
It's all over my bed.
4G.
You are purchasing a new car. The possible manufacturer car sizes and colors are listed. So you got Ford, GM, and Honda. You got compact, mid-size, and you got red, black, and green. Oh, I'm sorry, white, red, black, and green. So how many possible choices do you have for this first thing? How many for the size? 2. How many for the color? 4. What are you going to do to find all the different possible outcomes you could make?
You're gonna make it.
Multiply them together. What's it give you? 24. Alright, so 24 different ways. That's not too bad if we wanted to make a tree diagram out of it, it looks something like that. That's right there on the border of being too much, but there's 24 possible things. 24 possible items in your sample space. A pizza place offers 3 types of crust, 3 kinds of cheeses. How many different one-topping pizzas could we make? Did it say how many toppings they offer?
Yeah, oh, where it's behind the thing. Oh,
12 toppings. So if we just wanted one topping,
108.
what do we do?
3.
3 times 12 times 3. What's that give us?
108.
Now, 108 different pizzas, but that's only 108 different pizzas if you only order what?
One time.
One topping. If we order 2 toppings, how's that going to change this? Now, would that be 24 this time? Think about it, if you order a pizza. So we order our crust, we know we want thin crust, seamless. And then we order 1 topping. What's the first topping you want? Pepperoni. So you get pepperoni. We had 12 choices there, right?
Then we want pineapple.
Now we want pineapple. If we want pineapple, how many choices did we have?
12.
11, because we already picked.
You can get extra pepperoni.
We could, but that'd be another choice, wouldn't it? So, if we're not gonna get extra pepperoni, if we're just gonna get, so that'd be 11 choices here, and we still got times 3. What's that give you?
1,188.
How many different 2-topping? 188?
Yeah.
Close enough.
How many different 2-topping pizzas could you get? About 1,200. What's gonna happen the more toppings that we put on this?
The more pizzas we get.
It's gonna be more and more and more and more. So, what if we wanted how many different pizzas Pizza Hut can actually produce? How many different kinds of pizzas they could produce? Do we really wanna try to find that number? No, because that's just for the 1-topping pizzas. This is for the 2-topping. We could have 3-topping,
At the Lux
4-topping, 5-topping, 6-topping, all the way up to how many toppings?
12.
12. And then we start getting into what Gage said. Oh, well, we could put double pepperoni on it. We could put double pineapple on it. How many pizzas is Pizza Hut gonna be able to make? whole
Too many.
bunch. All right, different kinds of probability. Theoretical or classical probability. Theoretical or classical probability, this is how you find it. Probability, this is P, excuse me, this is P, this is your event. Whatever the event is that you're looking to have happen. Number of outcomes in the event, number of outcomes in the sample. And I'm going to write this down. We did this earlier this year. Favorable over total. When you're finding probability, it's favorable outcomes over total outcomes. Michael, that's the easiest way to remember it. Favorable over total. Now, when I say favorable, it's not always favorable, because if you're like finding the probability that a person's going to get cancer, well, that's not a favorable outcome, but it's the outcome that we're looking for. Does that make sense? Might be favorable for, maybe if you're dire enemy, you might want to wish something on them, but that's not nice.
That's not something you should wish on anybody.
Right, let's keep this to yourself.
Right. So this is classical probability. So when I flip a coin, what's the probability of getting a head? 1 out of 2. That's classical probability. If we flip a coin, is it always going to come up head, then tail, head, then tail, head, then tail, head? No. So this is classical probability. This is like mathematical probability. All right? What's the, without actually doing the thing or looking at anything, what's the probability? So it's always probability of whatever the event is, favorable over total. We can write them as fractions, decimals, or percents. Again, when you get to the bigger numbers, and you got crazy stuff, that's when you probably want to change it to a percentage, because it's going to make more sense if I tell Gage, hey Gage, it comes out to be about 30%, than if I tell him, hey, it comes out to be 325,290 out of 10,502,000. That makes no sense to anybody. So then it's better off to grab your calculator, change it to a percentage. You roll a 6-sided die, find the probability of each event. What's the probability of getting a 3? 1 out of 6. What's the probability of rolling a 7? 0 out of 6. What's the probability of rolling a number less than 5? 4 out of 6, which would reduce to what? 2 out of 3. And I don't mind if you don't change that to whatever. If you don't reduce it, it doesn't usually hurt anything. But your calculators will do that for you. Empirical probability. Empirical probability or statistical probability. Empirical probability is more about real life stuff. All right? Empirical probability, you're still going to find it basically the same way. Still the favorable over the total. But this time it's going to be, hey, we took a survey, and in our results we seen that 75 people said yes, and 25 people said no. So we're looking at the results of the survey instead of saying, hey, we flipped the coin and there's a 50-50 chance that you get head and tails. So empirical is looking at some kind of information from somewhere. Does anybody remember what's relative frequency mean? That's the percent. The frequency as a percentage doesn't necessarily have to be the frequency as a percentage, but. So we're gonna be looking at some kind of chart or something saying 75 out of 250 said this. And that 75 is gonna go on top, and then the 250 is gonna go on bottom. So it's still the same thing, it's just a different kind of probability. Does anybody remember what the third type of probability was? We'll get to it in a second. The company is conducting an online survey of randomly selected individuals to determine if traffic congestion is a problem in their community. So far, 320 people have responded to the survey. First of all, before I go any farther, what might be a problem? We talked about bias when we were looking at stuff like this. What might be a problem with doing this survey? If I get a phone call about traffic congestion, what might happen? I might hang up the phone. What might cause me not to hang up the phone?
Video.
If I have a problem with it. So probably most of these people that they're surveying is gonna say what?
I got a problem with it.
Hey, I got a problem with it. Otherwise, I wouldn't want to talk to you right now. I'd want to be doing my own thing. So if I'm get stuck in traffic for 2 hours on my way home tonight, and they call me and say, we'd like to take a survey about traffic congestion in your area, then I'm probably going to sit on the phone and talk to them. If I don't get stuck in traffic, I'm going to say, no, I got everything to do that. I don't feel like talking. So that might be a bias. What's the probability the next person that responds to the survey says that traffic congestion is a serious problem in their community? So we want the probability that they say it's a serious problem. How many total people did we survey? 320, that's on bottom. How many said it was a serious problem? That would be your probability. Again, you go out and you say,
30%.
look, this is a serious, 123 out of 320 people said it's a serious problem. Everybody's gonna look at you and go, no, that's not, they're not gonna care. But you change it to what?
38%.
38%, then they're gonna understand it better. Less than half. So that might be a thing. If you're trying to say it is, the way you guys are taking it now, you're saying, oh, it's less than half, so it's not a big deal. Well, if that's me, if we're trying to get something accomplished, you know, get stop signs put up or traffic lights put up or
30% of
something.
Skittles eater employees.
So we might want to not
You think it's cool?
have people looking at it that way. Law of large numbers. Law of large numbers. The law of large numbers just says, and this is what I was talking about flipping the coin. If we're flipping the coin over and over and over and over and over again, and we just keep doing it forever and ever, even though we know that we're probably never ever going to flip a head, then a tail, a head, then a tail, a head, and a tail, if we just keep flipping it over and over and over again, at some point, way, way down the road, are we going to get close to it being exactly 50-50? Yeah, unless there's something wrong with our coin. If it's got two heads on it and you're sitting there flipping it and you're getting heads every time, number one, that'd be pretty funny. I'd probably laugh at you. But that's all the law of large numbers says. It says if you do something enough times, at some point, you're going to get close to the theoretical probability. It doesn't actually work out this way, but Joey Votto for the Reds is a career 292 hitter. So next year, even though he might start off 0 for his first 20, we expect that over the long haul, using more bats, he's going to get close to what? 292. Now, it doesn't actually work that way because the older you get, then the less good you are.
He gets better.
He's getting better. I don't think so.
The Reds aren't getting better.
It could be, bro. The farm teams are decent.
The last kind of probability, subjective probability. Subjective probability is what like doctors use, and it's, I hate this, but it's saying use an educated guess. It's not really a guess, all right? Doctors, if you go to a doctor and they're guessing on what you have, then
But it's educated.
Yeah,
then it's not a guess.
it's based off of information they already know.
Right, and that's the way it should be. So an educated guess is sort of a stupid way to say it.
Can't you just say
Say what?
inference?
Inference. Well, that's trying to use that without using the word inference. So they're making an inference. Hey, from an assumption, from all the stuff that we've seen in the past, this is what we think. Okay? So a doctor, whenever those doctors, they come in, the nurse comes in first and they write down all your stuff and what's wrong with you and everything, and then you sit in there and you think, this stupid doctor, I know he's out back smoking a cigarette or something. He's just leave me sitting here, been sitting here for 20 minutes. Hopefully not. Hopefully the doctor's doing what?
Working.
He's working. He's going in, looking up on the computer, looking up and stuff. Hey, Gage has this and this and this. All right, what could this be? All right, so his throat hurts. He's got a temperature. He's sweating a lot. Oh, so he must have a broke arm. So if your doctor comes in and does that, then you know you should be going somewhere else. Classify the statement as an example, classical, empirical, or subjective probability. Probability that you will be married by age 30 is about 50%. Is that classical, empirical, or subjective? Could be subjective, but it's probably empirical because they've looked at other things from the past
So
and see that, hey, most people are married by, or 50% of all people are married by the age of 30.
see?
The probability that the voter chosen at random will vote Republican is, this one I know for sure. That's empirical for sure. Because they've looked at everything else, right? I don't know why. So I could just make up something and say, oh, yeah, Gage, you're going to be married by the time you're 85.
Subjective. Good job.
You're right, that would be subjective, I guess. I'd be just making fun of it. The probability of winning a 1,000 ticket raffle with one ticket is 1 out of 1,000. That's classical, right? Because we're actually using the numbers, that's classical.
And in person it was $63.
Range of probabilities. All probabilities have to be between 0 and 1. All probabilities must fall between 0 and 1. So if you get a probability that's negative 0.5, you messed up. If you get a probability that's 2.8, you messed up. When you're looking at probabilities, probability of any certain event, all the probabilities of any certain event always got to add up to one whole. So if we're doing some little chart and we're saying, all right, what's the probability that you get a 1? What's the probability that you get a 2? What's the probability that you get a 3? What's the probability you get a 4? And those are the 4 events in this thing. All of those probabilities together must add up to one whole. If the probability is less than 0.05, that means 5% or less, then it's unusual. Not 0.5, 0.05, right? Then it's considered unusual. Guaranteed next test, there'll be something on there and it'll say, is this an actual probability? And they'll have some chart like this. And the probabilities might not add up to 1, or they might, one of them might be a negative or something. And then you're gonna say, no, this won't work because whatever. Complement of an event. Again, the complement of an event, easiest way, I'm gonna put all these up here. I went too far. So all of these are just different ways to write this. Easiest way to think about this. The event plus the event's complement, that's what this little tick mark means, always has to equal one whole. The event plus the event's complement always has to equal one whole. And that's what this first one says. Then the rest of them are just offshoots of that, just subtracting something off or whatever. We talked about this at the very beginning. What's the probability of drawing a queen from a deck of cards? 4 out of 52. So what's the complement of that?
48 out of 50.
So what's the probability of not drawing a queen out of a deck of cards?
48.
48 out of 52. That's easier. So remember that this little mark, that little tick mark, the little prime mark, is what means the complement. So if they say, find the complement of getting the queen, that means you want whatever it is not getting the queen. You survey a sample of 1,000 employees at a company and record the age of each. Find the probability of randomly choosing an employee who is not between 25 and 34 years old. So we want not between 25 and 34. What would be the easiest way to do this?
1,000 minus 360.
Take 1,000 minus that. 1,000's going to be on bottom still, right? And you subtract that off, because that's the ones that we don't want. What's it, like 634, is that right? 634. Guess what all the rest of these add up to equal? That there. So that would be the complement of that probability that they're not between that age. Did I do the math wrong? 630. Oh no, that's they're working it out completely. 634. Why even? I guess they're just explaining it to you. Probability experiment consists of tossing a coin and spinning the spinner shown. The spinner is equally likely to land on any of the numbers. Use a tree diagram to find it. So if we're tossing a coin, what could you get on the coin? Tails, you could get what? Heads. What could you get, if you flip a tail, what could you get on the spinner? 1, 2, 3, 4, so on, so on, so on, right? So the tree diagram, it looks something like this. Again, this is our sample space. Those are all the possible outcomes. Tossing a tail and spinning an odd number. So we got tail and spinning. How many total outcomes are there? 16, is that right? How many odd numbers with a tail? 4. Everybody agree with that? 1, 2, 3, 4. So what's the probability of tossing a tail and getting an odd number? 4 out of 16 or 1, 4, 25% of the time. Your college identification numbers, now a little harder stuff. Consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when you randomly generate 8 digits? When you're doing something like this, and we're going to do a lot of hard stuff like this throughout this chapter. It's got 8 digits, so I'm going to do this. 8 blanks. What could we get on this first blank?
0.
Or any of those, right? How many numbers is that? 10 of them. So how many choices you got for your first number? 10. How many choices for the second number?
10.
10. Third number?
10.
Fourth number?
10.
Fifth number?
10.
Grab your calculators. Sixth number? How many total possible outcomes?
100 million.
Huh?
100 million? I don't know. 10 with 9 zeros.
10 with 9 zeros? So a 10 with 9 zeros or a 1 with 9
Or
zeros?
1 with 9 zeros.
Everybody agree with that? A 1 with 9 zeros?
Or 8 zeros? I don't know.
It's 8 zeros.
It's 8 zeros?
I can't count.
A 1 with 8 zeros, is that what we're going with?
Yeah.
1, 2, 3, 4, 5,
100 million.
6, 7, 8. So 100 million, is that right? Now what's the probability that you get your certain number?
1.
1 out of 100 million. Now, those are big numbers, or one of them's a big number. Would we want to change that to a percentage? Probably not. It probably looks better that way. 1 out of 100 million. So if somebody's going to steal your number and they just randomly punching it in, they got a 1 in 100 million chance of actually getting the correct number. What happens, what could change that? Some of them might say that what can't happen here? You can't repeat, so if your first digit is a certain number, then 9 choices, then 8, so on, so on, so on. License plates. Oops. Now odds will be the last thing. State of Ohio, I'm not sure what it is now, but the state of Ohio, it used to be, you had 3 letters and 3 numbers. How many different license plates, if we just go with that? 3 letters, so letter, 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 number, number, number. How many different license plates? Now they've switched it up because there wasn't enough license plates. So,
6 letters, 6 letters.
so how many possible outcomes are there for the first letter?
26.
26. How many possible outcomes for the second letter? 26. Do they say that they can't repeat?
No.
How many possible outcomes for the third letter?
26.
How many possible outcomes for each number? Be careful now.
10.
10.
With 0, you could add 10, right? How about second number?
10.
Third number?
10.
Somebody do all that for us. 17,576,000
Yeah.
Now, why did they change up the license plates?
There's more people in that.
Because apparently there's more than 17.5 million people driving in the state of Ohio, or,
More than
shouldn't
that.
say that, more cars than that. All right, because maybe you work for a company that as a driver, well, they have their car and you have your car, but there was more than that. Now, let's go back to this for a second, because I'm gonna tell you that's not right in the state of Ohio. Because some of these numbers, guess what can't happen?
Can't repeat.
They can't use them. All right? Certain numbers that they won't use. What numbers do you think they might not use?
6, 7, 9.
Or letters. Let's go with letters first.
ASS.
Right. So certain order they for sure won't do, right? Even though something like that, I think I have seen that before. As long as you don't request it and it just comes up randomly, I don't think there are some letters though that they won't use at all.
Oh, X.
O. Why won't they use an O?
Zero.
Because it looks like a zero. You can't use both of them. So I can't remember if it's a zero or the O that they won't use, but one of them they don't use. All right, and an I. Some I's they don't use because it looks like a one. All right, so if they decide, hey, we're gonna do our I's like this, then maybe, but let's not.
Doesn't it always go 3 letters, 3 numbers?
It used to be that way. Now it's
I
different.
was saying if it does, then you could use eyes or if it's on the left
Well,
side.
sure, mine is
No,
three letters.
but see, they don't do that.
It's not always here.
So there's certain things that they don't put in here. Then you're right, there's certain things also that they will not write in here. Like I think the word, that word, they won't put in, but if they don't use O, that won't matter. Can't remember what the other one was.
They put window on
And that's the other thing, how could we even get it higher than this? Because you can do what?
there. All of it.
You can personalize it, all right? So you could personalize your license plate, and that'll make it even more. The idea, that would make it easier for the state if you personalize it. You know what the state does to thank you for personalizing it?
Makes you pay more.
They make you pay more, they charge you more. When I was in college, the state of Virginia wanted you to personalize your license plate because it made it easier for the cops to identify you. And so it cost more to get just a random license plate than it did to have it personalized. Odds. You see odds a lot with like horse racing. So if you watch a horse race and it says Blue Stallion is a 7-2 or has 7-2 odds. That means if Blue Stallion runs, they're going to win 7 times and lose 2 times. So how many total races is Blue Stallion going to race? 9. All right, so if we want to change this with odds of winning is always going to be wins, losses. It's wins compares to losses. And then odds of losing just turns that around. So 7 wins compared to 2 losses. If we wanted to change that into a probability, all we do, the probability of this horse winning is 7 wins out of a total of how much? 9 races. All right? Is that a horse you'd want to bet if the odds are 7-2?
Oh, yeah.
Real good chance you're going to win. The bad thing is, this also means you're going to pay how much?
More.
You're going to pay $7, and how much you're going to win?
$2.
$2.
So,
So you're going to lay your $7 down
You're gonna
there,
lay it on one spot, like 4.
and if you win, you're going to win 2.
Got no 4 and 3 horses.
So it'd probably be better off if you bet some horse, maybe that was like 1 to 50. Because now you're gonna lay down $1, and if that horse happens to win, you win
Underdog.
50. Alright? But the main thing here is know how to change from odds into a probability. So you just have to add them. What if I gave you this? What if the probability of the horse is going to win is 3 out of 5? What would its odds be? How many wins? 3. How many losses? 2. So this right here says the same thing as that, only one's in odds, one's in probability. That's your assignment, most of it not real difficult. If I can find your test, I'll show them to you.
Not really. It's just a lot of like spread out questions.
1, 2, 3.
We've got about 8 minutes, please. Do not walk out of here with your
I
test,
didn't even see the one.
because I do not have them all recorded yet. So if you walk out of here with your test, guess what your grade's going to end up in?
0.
It's going to be a 0. Do not walk out of here with it.
I don't know what mine.
You don't want yours?
Well, I do, but I don't. I don't know if I should look at it.
They're like, I'll pull up the questions.
I got to be first.
Oh, labels. Those matter.
What I get?
Yeah. Wait. Man.
Not much. Oh, gee.
What a question mark for?
You don't know what you... I just didn't do that question.
I put X bar.
How weird.
Zoe, I'm sitting here looking for your test. That's why I was standing above you like that. Hang on to it for 1 second so I can. Some of them I put question marks on if maybe I didn't understand quite what you were trying to explain. Might have put a question mark. You probably got lucky because I probably didn't take off any points.
Bro, how weird. This stuff is cool.
All I can tell you is, I guess I'm just and then this one, I guess. Did you give me a bonus right? I didn't even do the test. Plus one.
You said you can pick a tablet.
Y'all really said
It can't be
it.
worse than the version you got a 4.
You see what the slide again?
I got 91.
I know it's gonna happen.
Say I got 4.
I think he slid two.
On the bonus, again, if you get a bonus right, I put a plus beside it. If not, if there's not a plus beside it, then
I
it
didn't
wasn't
get
right.
4. I got 3.
I got both of them right. I got my grade
Yeah,
out.
I think he slid too late anyway.
I didn't get. What, Chip? Which one did you get wrong?
The bottom one.
Yeah, we just plug that in your calculator. And then you plug that equation in your calculator, you times it by 1.
You just didn't do
Oh.
that.
That's okay.
I didn't like that my stuff right.
Hey, Sam. Everybody do better than me.
I just remember, I didn't study guide, and I sat there and I never studied guide. But my mom
Stay
watched
that
me
way.
cry because I hate math.
I gotta do this homework. God, it's 100 problem homework videos.
Like third.
Graduates and valedictorian.
So, I always got bad grades in math because I tried to know my work.
Bro, it's so cold.
A lot of problems.
It's critical problem.
36.
I came from your transitional class.
Alright, on the homework. If you try, I'll let you cut it off a little bit, but don't cut it off.
30 questions.
Right, don't just stop at 1 through 36, alright? So try some of the first ones and skip some of them that are the same to get to some of the other ones.
If you think about it, it's only 56
Does that make
questions.
sense?
I get extra credit if I don't
It's
follow.
only.
Should be the same.
I just
Tell me if I'm higher.
Try some of each type of problem on the homework.
He's the best kid, dude.
That's an offensive word. Now that I say that
That's a
word.
derogatory term.
It's a little person.
Yeah,
It's a little person.
Nah, you know, micro wrestling? Psycho calls himself a midget all the time.
Well, I said some.
I bet you probably.
I want to watch that so bad.
My mom ran
saw
that.
it.
I'm gonna go to one. I'm like, sure, but
Yeah.
we didn't go. Midget wrestling.
Micro wrestling.
Oh, my bad.
Definitely major wrestling. It's recording. You're saying.
This is
Recording.
the, this is no collecting. I got
50
three,
years
so.
of like.
I feel like you're